Good morning, students. Today, as discussed earlier, we will talk about collision handling techniques. So, as we already noted in the previous class, we will talk about chaining. We will talk about open addressing, which can be further divided into linear probing and double hashing. So, we will start off with chaining. This is a very simple technique. So each cell of the hash table here points to a linked list. Okay, of all the elements that are mapped to a particular cell of the table. So the important points to note here is that the colliding items are stored outside the table, and naturally, although this is a simple method, it requires additional memory. Right, because you have to store the colliding elements outside the table. Okay, so a simple example could be as follows. Let's say the key is birthdays and elements are names. Okay, and your hash function obtains a hash value as month of birth modulo 5, something like this, and you have 5 places. In the hash table. So say for instance, there is this guy Sue who is stored in a linked list with 2 elements, the key value and the name. And this linked list ends here. Say there is another cell where you have one entry of John, and then there is a colliding entry which becomes the second member of the linked list, associated with that cell. Okay, so in this way you can build a collision free hash table, okay, where each of the cell of the hash table is not used for storage. What is used is actually a linked list connected to this particular cell where the hash value maps the key to. So if you recall, the adjacency list representation of graphs, okay, that also can be thought of as a linear chain. As an example of chaining, right? Because there also you have nodes, and to each node there is a linked list of other, to each node is connected a linked list of other nodes to which this node has an edge to. So you can always imagine the adjacency list representation of a graph as a chaining formulation of the hash table technique. So the caveat here, okay, you need additional memory. However, the more important problem, okay, is that everything might collide on a single cell. Worst case, right? Say in the previous example, all birthdays that you try to hash, the birth month actually collides on say 2 or 3, whatever. So in such case, you land up into a single linked list, right? So this is a very big caveat. Okay, in the worst case, you can land up into a single linked list because everything collides on a single key, and therefore mm, you land up into one single linked list of size n. So therefore your search complexity again becomes order n in the worst case. So this is something which is probably that we would try to avoid. Okay, so therefore the second type of collision handling technique came into existence, and this is actually like used more in practice. This is open addressing, and we will first talk about linear probing. So open addressing is an idea where the colliding items are placed in different cells of the table. Okay, so the colliding items are placed in different cells of the table. So basically the word open means you open the other locations in the table to handle collision. Fine. So this is what is the idea of open addressing. Now, the first type of open addressing that we will talk about is linear probing. What do you do here? So colliding items are stored in the next circularly available cell. Okay. So testing of cells is cells available or free testing if cells are free is called probing, and that's why the name. Linear probing. So we take a small example to illustrate the case. Say for instance your hash function is x mod 13, okay, and we want to insert the following elements. And let's say we have a running table like this. Okay, so that's why modulo 13. So this is modulo number of cells, okay, modulo the number of cells available for storing or hashing the elements. Now say the first element that we see is 18. So 18 goes in this position because 18 mod 13 would be 5. Okay. So the next element is 41. So this will go at position 2 because 41 mod 13 is 2. Now the next element is 22. Okay. So 22 mod 13 is 9, and so 22 goes and sits here. Next is 44. So 44 modulo 13 is 5. So, but the location 5 is already blocked by 18. So therefore, you proceed one step, okay, and you probe the next cell. You see that the next cell is free. You place 44 here. Next, 59. So 59 modulo 13 is 7, and therefore it sits here. Okay. Next is 32. So 32 modulo 13 is 6, but cell 6 is already blocked. So you probe the next cell that is also blocked, and then finally the 8th cell is free and you are able to place 32 there. Then 31. 31 modulo 13 is 6, but 6 is already, sorry, is 5, but 5 is already blocked. So now you move 1, 2, 3, 4, 5, and in the 6th place you find a free cell and put it there. Now similarly 73 moves like 3 locations and comes and sits at 11. Okay, so in this way you compute. So basically you try to see, check, as long as there is no free cell, you keep on probing, and at a point in time where a cell is obtained, you place the first free cell is obtained, you place the element there. If you have exhausted the whole list and could not find a proper place to insert, then you have to throw an exception that there is no space left in the cell. So there is one caveat here, that the colliding items can lump together. Okay, and this lumping can cause further collisions. Fine. So this is a caveat of this particular way of hashing elements. So the linear probing we will talk about in a little more detailed fashion, because as I said, this is one of the most well-known ways of hashing these days. So how do we search? Probing, search. Okay, so we have to search the element key, sorry, search for the key, search for the key, say k. Okay, let us call it find element corresponding to the key k. Okay, so what we do, we start at cell hk, right, and probe the consecutive locations until one of the following conditions are satisfied. Either an item with key k is found, or an empty cell is found, which means that such an element is not present in the list. Okay, because you have been starting from the hkth position of the cell, and you have been looking one after the other, you have been probing the next cells, and if that element had to be there, it would have been in one of the next cells. But if you encounter an empty cell without encountering that key, that means that key was never inserted in the hash table. All n cells have been probed unsuccessfully. So either you get the element or you encounter an empty cell, which means the element is not there, or you have exhausted looking at all the cells and are unsuccessful. So you can also write a small pseudocode for this. P is the probe, I is the hash value. You look at the array element at index I. Now, if is an empty cell, then return no such key. If C key is equal to K, then return element. Now you advance I and you advance your probe until and unless you have exhausted everything. Now once this entire while loop is executed and you have not returned, that means you have unsuccessfully probed all the cells and therefore finally return no such key. Okay, as simple as that. Linear probing, deletion. Okay, so deletion, which we'll call remove K, could be expensive. Why, we will see with an example. Say for instance, for the same hash function, hx equals x mod 13, you have the following state. And now say you want to do remove 15. So this means that the new reorged cell conditions or cell states should be as follows. Because 15 hashed to the index 2, because 15 mod 13 is 2, and then after that 2 came, so 2 could not take its place, its actual place, and since 2 could not take its actual place, 3 could not even take its actual place, and since 3 could not take its actual place, 4 could not take its actual place, and so on and so forth. This happens. So therefore, if you remove 15, you will have to push back the entire set of elements one index earlier. So this should be the ideal situation. However, you see that this is pretty expensive because all the elements now have to be shifted left by uh, one cell, okay, and this could be pretty expensive. So what we do, so in order to, like, minimize this cost, what we do is whenever we delete, say, some element, we make that space available. We make the space available. So 2, we mark it as A, okay, and then after that the rest remains as is. Now from time to time, we clean up. Rather than cleaning every time, we wait for a gap, lot of A's have been accumulated, say, then at a particular point in time, we do a cleanup when a lot of available spaces are marked on the cells of the hash table. Okay. So during cleanup, we remove all available cells and reorder items. So this A here marks as an available cell. Now we will talk about insertion. So let's call it insert item at key position K. We want to insert the element O. Now here start at cell HK, probe consecutive elements until an empty or available due to deletion cell is found, then store the item there, or all n cells have been probed. So table full throw exception that the element cannot be added. Let's again take an example. Let's say we have the current state of the table as follows. And now say we have to do insert item 3. Okay, so in this case again the same hash function. Okay, so in this case the 3 modulo 13 will be 3. However, 3 is already blocked, so you move to 4, 4 is blocked, move to 5, 5 is blocked. Now move to 6, and 6 there is an available cell. Okay, so therefore this available cell is used to place 3. Okay, so just one point here, that the find element, okay, that you will probably also need to use in your insertion algorithm, find element, okay, cells with available are treated as filled, that is the search continues. Okay, so basically if you are just doing the find element, then every cell marked as A is also thought to be an occupied cell, and the search continues. So this is not considered to be an empty cell. Okay, however, as you understand that you can simply modify the find element algorithm to also do the insertion. In that case, in such a case, an available cell or an empty cell can be used for the purpose of insertion. Okay, however, when you are doing simply find element in isolation, then you have to observe a cell having the entry A as a filled cell. Okay, so and the search will continue in the hope of finding the element, unless it, you know, encounters an empty cell or the entire n cells have been already unsuccessfully investigated. Now, as I already said, that there are some disadvantages of linear probing. Okay, so people suggest for so the colliding items, as we said, that could lump together, and that can actually reduce the performance by increasing the number of collisions. So people have thought of some possible extensions. And one of the easy way to do it is that instead of probing successive elements, what you do, you compute the ith probing index hi, and this is dependent on I and k. Okay, so basically HIK is now computed as HK, which was the original hash function, plus some function which is dependent on I and k. Now there could be various choices of FIK. Could be fixed increment C, which is HIK equals HK plus C into I, where C is a constant. Now, changing directions. Where HIK is equal to HK plus C into I minus 1 power I. So you change the direction. Okay. If the current direction is forward, you make it backward. If it is backward, you make it forward. Double hashing. Where HIK is equal to HK plus I H prime K. And this is something that is also quite frequently used. So now here, as you understand, you use two hash functions. One was the original one and the other is a new hash function that you introduced. That's why the name double hashing. So let us take a very simple example of double hashing and see how it works. Let's say that n is equal to 13 and hk is equal to k mod 13 and h prime k is equal to 7 minus k mod 7. Okay. Now suppose I again have the 13 cells. Let's draw it in a more shrunken way. Let's draw it in a more shrunken way. We can do it, do everything in a single slide, then it will be easier for us to understand. Now this is the double hashing computation table. So let's say our first k is 18. So 18 mod 13 is 5 and 7 minus 18 mod 7 is 3. Okay. So now you start computing the probe. So the first probe is 5 plus, as we said, I into h prime k. Okay. So hk plus I into h prime k. So it is 5 plus 0 into 3, that is 5. So location 5 is available. So therefore you put 18 in location 5. Next comes 41. Okay. So your hk in this case is 2 and h prime k is 1. Okay, so you make the first probe at 5 and it's correct. So now here your computation is 2 plus 0 into 1, that is 2. So note that this 0 that I am writing here is the value of I, and this will be updated. So I is from 0 to n minus 1. And as I had already told you that the new double hashing is hk plus I h prime k. This is hi, where I ranges from 0 to n minus 1. Next, 22. So hk is 9, h prime k is 6. The first probe that you make is 9 plus 0 into 6, that is 9. Therefore, the first probe is at place 9, and at 9 you place 22. So here for 41 we found that the probe ends at 2, and therefore we place 41 at 2. Now comes say 44. So now you have again hk as 5 and h prime k as also 5. Now the first probe you make is at 5 plus 0 into 5, that is 5. However, 5 is already taken. So then 5 plus, now you vary I. I was 0, now you have I as 1, and 5 plus 1 into 5 is 5. The sum becomes 10. Okay. So the first probe you make is at 5, then second probe you make it as 10, and 10 is a free location. So therefore you can put 44 in the 10th location. Next, let's say we have 59. So hk is 7, h prime k is 4. Okay. Now you have 7 plus 0 into 4, which is 7. 7 is an empty location, so you can place 59 in location 7. Next comes 32. So 32, hk is 6, h prime k is 3. So the number of probes is 6 plus 0 into 3, that is 6. Now say the next number is 31. So the first probe is again at 5. Okay, and hk is 5, h prime k in this case is 4. So therefore the first probe happens at 5 plus 0 into 4, that is 5. This is taken, so we cannot use this. Next probe, 5 plus 1 into 4, that is 9, but place 9 is also taken, so we cannot use this. So then we have 5 plus 2 into 4, that is 13, modulo 13 is 0. So 0 is not taken. So you have the proof 5, 9, and then finally 0. So you can place 31 at location 0. Similarly, you continue. Say it's 73, it's 8, 4, and it is 8 because 8 plus 0 into 4 is 8, and location 8 is free, and therefore you can keep 73 in location 8. So in this way, you compute the double hashing by varying I and computing two hash functions, one after the other, to actually spread apart the elements in the hash table. Okay. So this is the idea of double hashing. Now, can we make some comments on the performance of hashing? So one thing is very clear, that the worst case insertion, search, as well as removal can take order n time, okay, where n is the number of elements. Okay. So this will happen when all keys collide in one single cell. Okay. So the load factor that I talked about last day is an important indicator of the performance. Which is n by capital N, it affects the performance. And actually, assuming that Hash values are like random numbers we can show that the expected number of probes would be 1 by 1 minus alpha. Okay, so this is the expected number of probes. So the proof of this is beyond the scope of our syllabus. However, you can keep this as a rule of thumb that given the load factor alpha equals n by n, and there is a set of hash values which are treated as random numbers, then the expected number of probes that you need to actually search or insert or delete an element is 1 by 1 minus alpha. Now, in practice, hashing is pretty fast given that alpha is less than 0.85. Okay, and typically it has an order 1 running time. Some applications in computer sciences small database design, compilers, compiler construction, so you will come across, when you study compiler design, you will come across something called a symbol table, where you will see the use of hashing and also implementing browser caches. Okay, so these are some of the examples where hashing could be, example applications where hashing could be used. So we'll stop here, and in the next class, we will talk about a special type of hash function which tries to minimize the collision to the bare minimum possible. Okay, these are called universal hash functions, and we will talk about them in the next class.